Continued in section 1.3, we're going to talk about a couple of different types of limits that you can also evaluate by direct substitution in certain circumstances. So the first one is the limit of a function involving a radical. If we let n be a positive integer, the limit below is going to be valid for all c when n is odd, and valid for positive c's when n is even. So the limit as x approaches c of the nth root of x is equal to the nth root of c. So we can take the limit as x approaches c of an odd root by direct substitution for all c, but we can only do this for an even root if c is greater than 0. And it may be that a limit doesn't exist or something along those lines if it's an even root with a negative c. So if we wanted to evaluate the following limits, the limit as x approaches negative 8 of the cube root of 8. You can see that this is an odd root. So we can do this one by direct substitution even though c is negative, and it would be the cube root of negative 8, which is negative 2. We could take the limit as x approaches 12 of the square root of x, even though this is an even root. The index is understood to be a 2 here. C is positive, so that doesn't matter. So this is the square root of 12. And if we wanted to evaluate this, or to simplify this, 12 could be written as 2 times 2 times 3. That's its prime factorization. And this pair of 2's can come out front. So this is 2 times the square root of 3. One thing to keep in mind in this class is that whenever possible you want to give an exact answer. So 2 square root of 3 would be an exact answer. Plugging the square root of 12 into your calculator and rounding and giving a rounded decimal is not an exact answer. So unless you're told otherwise, do not round. Composition functions can be dealt with using direct substitution in some circumstances as well. So you can think of a composition function as kind of an assembly line. So f of g of x is f evaluated at g of x. So if you have x equal to some c, you can think of it as first putting it through the g function. So I'm going to think of this as like an assembly line with a machine. And the limit as x approaches c of g of x is L. So an L is going to be the output of that. And then you're going to take that L and pass it through the f function, or the f machine if you want to think of it that way, and the output ends up being f of L. So that's why the limit as x approaches c of f of g of x is actually f of L and it's not f of c. So let's look at some examples and see what that looks like. If you have something like this, the limit as x approaches negative 1 of the fourth root of x plus 17, f of x would be the fourth root of x, g of x would be the x plus 17. So the function on the inside has to be defined at whatever this value is. So can you plug negative 1 into x plus 17? Yes, you can. That would give you 16. But in order for this to be well defined and to be able to be evaluated by direct substitution, whatever you get from plugging in c here has to be part of the domain of this outer function. So when I get that 16, can I take the fourth root of it? Is it the even root of a positive number or just an odd root? And the answer in this case is yes. So we can actually evaluate this one by direct substitution as well. Remember, my f of x, you could think of it as the fourth root of x. My g of x, you could think of it as x plus 17. You don't have to get bogged down in those details every time, but it is kind of the underlying picture here. This would be the fourth root of negative 1 plus 17, which is the fourth root of 16, which we know to be 2. Now this one's super easy because it's just a polynomial raised to a power, and polynomials are defined everywhere, and you can raise any number to a power of 7. So this one is definitely able to be evaluated by direct substitution. But if you want to talk about the composition here, f of x would be x to the 7th, and g of x would be x minus 2. So this would be 3 minus 2 to the 7th power, which is going to be 1 to the 7th power, or just 1 as your answer. Now we're going to talk about some special limits of trig functions. Before we get too deep into this, you definitely want to make sure and review the unit circle and the special 30, 60, 90 triangle and 45, 45, 90 triangle. Those will be in the trig review video. But we're going to go ahead and talk about limits of trig functions, so if you need to pause and go back to that review, now would be a good time to do so. So the trigonometric functions when you go to evaluate the limit as x approaches c of one of the basic 6 trig functions, sine, cosine, tangent, cotangent, secant, and cosecant, basically as long as c is a real number in the domain of whichever trig function you are looking at, you can evaluate that limit by direct substitution. So for example, sine and cosine, their domains are from negative infinity to infinity, so you can plug any value that's a positive, or sorry, that's a real number into sine and cosine. The other functions have some limits to their domain, so as long as it's in the domain, it can be plugged in by direct substitution. So for example, if I wanted to find the limit as x approaches 0 of cosine of x, this is just going to be cosine of 0. So if I were looking back at my unit circle, I know that the angle 0 is right here, and we usually put these in radians. So the cosine is the x value here, so this cosine is going to be 1. Similarly, if I wanted to look at the limit as theta approaches pi of sine of theta, notice instead of an x, I have a theta here. It's just a placeholder variable. As long as you're consistent, it doesn't matter. This is going to be sine of pi. And if you go back to your unit circle, pi is over here. So the sine of this is the y value, which is 0. So this is 0. And the limit as x approaches pi over 2 of cosecant of pi over 2 is cosecant of pi over 2. So that's going to be 1 over sine of pi over 2. And if you go back to that sine of pi over 2 is the 90-degree angle, sine is the y, so that value is a 1. So this is 1 over 1, which is 1. Now, if you try to do something like, for example, the limit as x approaches pi over 2 of secant of x, this would be secant of pi over 2, but this does not exist. So pi over 2 is not in the domain of secant of x. So we can't evaluate it by direct substitution.